Okay. Can you hear me? Hi, everyone. So, my name is Yoav Weiss. I'm the CTO at Tabuki. And today I wanted to talk about the gas station network and how we decentralize meta transactions. So before we start talking about the gas station network, let's try to understand the problem we are facing. And the problem is gas payment and having to hold Ether. So DApp onboarding today is totally broken. If you want to onboard a new user who doesn't come from the crypto space, he needs to jump through several hoops. So first, okay, what happened here? Yeah. Okay, so the user first needs to go to an exchange. Because he doesn't have any Ether to pay for the transactions. Then he needs to pass KYC at the exchange before he can do anything. This can take a couple of weeks. Then he needs to transfer money from his bank, if his bank is willing to do so, to transfer money to the exchange, then use it to buy Ether at the exchange, install MetaMask on his browser, finally move the funds from the exchange to a MetaMask, and only then get to the DApp. By that time, we probably lost the user. So we may be the users for dApps, but normal users are not going to come. So the question is, how do we move from this to that? And that's the problem we're trying to solve here. And it turns out that the community has been doing a lot of work solving this problem already. All of these solutions are based on something called meta transactions. With meta transactions, the idea is quite simple. You put a relayer. It's a server that you put between the blockchain and your user. So now, when a user generates a transaction and doesn't have Ether, he can sign the transaction regardless, send it to a relayer. The relayer wraps it with another transaction, and then sends this transaction to the blockchain because now the gas is paid for. So the relay pays for the transaction. So what's wrong with this picture? Why did we need anything more? So the problem with meta transactions is that it's a centralized solution, and we don't like that. So first of all, the relayer is a single point of failure. When you put a relayer in front of your DApp, if the relay dies for whatever reason, let's say someone tries to attack it in order to take your DApp down, then your DApp is essentially dead. It exists on the blockchain, but there's no way for your users to communicate with it, which means that it's no longer decentralized. And the other big problem we have is that it requires blind trust. The relayer becomes a part of your trust base, whereas until you added the relayer, all of your trust was embedded in a smart contract, which is open source, can be verified on the blockchain. So all the users can look at it and know exactly what they are facing. They know exactly what the app is doing, whether it's going to be fair. But once you add the relay server in front of it, you lose that, because now the relay can decide, for example, to favor one user over the other, or it could just decide to censor certain types of transactions. The user simply has no way to know. So it becomes a trusted component, and we don't want that either. And this goes against our core beliefs at Tabuki. We don't want single point of failure, and we certainly don't want any blind trust in any component. We want everything to be verifiable. So we looked into decentralizing that. And it turns out that the community has been working on that problem for a while. But all of these attempts were going in a direction that ended up having to solve a difficult problem. What they tried to do is to create a secondary transaction pool. So you have a transaction pool of gasless transactions, and you have relayers competing over them, mining from this pool, taking transactions and signing them to pay for the gas and delivering them to the blockchain for a fee. While this solution may sound reasonable, once you start looking into the details, you realize that there's a synchronization problem that turns out to be quite hard to solve. The problem with synchronization is that if a relayer needs to, then a relayer will always pick the most expensive transaction because that's what's profitable for it. So it will take the most expensive transaction, put it on the blockchain. All of them will do so. The first one is going to be successful. The other ones are going to get reverted and actually lose money because the transaction can only be put there once. But most importantly, the cheaper transactions are never getting to the blockchain. So this solution doesn't fly. And after we saw how hard it is to solve, we thought about the problem again, and we realized that maybe we don't really need to solve this problem. If we can change the problem definition and get to a solution without going through this synchronization issue. So we wrote EIP 1613, which does basically that. We realized that the sender is already, the user is already most incentivized to put the transaction on the blockchain. He just lacks the tools to do so. So we thought, what is the minimum tool set needed in order to support that? And it turns out that what you need to be able to do is to discover relays in a decentralized way. So you can select a relay from a pool, and then you need to be able to verify the service without waiting for mining and in a trustless way. If you can achieve these two goals, then you can turn the problem upside down. Instead of having a transaction pool, you have a relays pool, and you let the sender select the relayer. And that's what we did in our solution. So the solution revolves around a central smart contract called Relay Hub. It's a singleton. There's exactly one on the entire blockchain. All the relays have to register with Relay Hub. They have to place a stake, which is used to guarantee their service quality. It has to announce its fee, so everybody knows how much they need to pay for the service of this particular relay. And finally, the URL, so that clients know how to reach it. And as the relay is being used in the system, the Relay Hub contract also emits useful events that can be used to calculate reputation for relays, and knowing when, so all the clients can look at relays and know which ones are good and should be used. But all of that would have been useless if we couldn't solve the immediacy problem. If we needed to wait for mining every time we put a transaction in order to know that the service has been provided, then the system wouldn't work. What would happen is if you have a small number of, even a small number of non-functional relays, the situation would be something like this. The sender connects to the sender picks a relay, sends the transaction, then waits a few minutes until it realizes that the transaction is not getting mined for whatever reason. So it drops it, moves to the next relay, waits for a few minutes again. Have just a few of these makes the system useless. So we figured out a solution for the immediacy problem. The way it basically works is when the user wants to send a transaction, it finds a relay in Relay Hub and agrees to pay the fee. So it connects to that relay, sends the transaction. Now the relayer looks at the Relay Hub and then checks the destination contract, the recipient, making sure that it's willing to accept the transaction and pay for it. Once it figures that out, it does two things. So one thing is it puts it on the blockchain, so it will get mined. But the other thing that it does concurrently at the same time is return the signed transaction, resend the signed meta transaction back to the user. So now the user doesn't wait for mining. The user can just look at the transaction. The client checks the transaction. It makes sure that it is exactly the transaction it requested, that it is properly signed by the relayer. The nonce for the transaction matches the current nonce of the relayer, and that the relay's balance is sufficient to pay for it. With these conditions, the user knows that the transaction will be mined if it is put on the blockchain. And in fact, the user could just take the transaction and put it on the blockchain itself. So he doesn't need to wait for to trust the relayer to put it there. There are still a few corner cases, a few ways in which a relayer could return a signed transaction, but then do something to make the transaction fail on the blockchain. But luckily, all of these attacks are provable on the blockchain. There are ways to provide a proof for it that can be verified by the contract. So we added a penalize function to Relay Hub, where anyone can find a proof that the relay tries to cheat a user, put these transactions on chain, and then take away the stake. So the penalize function will kick this relayer out of the system and give the stake to whoever proved it. And the client doesn't even need to worry about that. All the client does is take the signed transaction and give it to another relayer, or maybe more than one, and forget about it. Because now the relayers are incentivized to watch each other. So if one relayer catches another relayer trying to cheat, they are going to take away stake. There's a strong disincentive for cheating in the system. Now, I wish we had more time to explore the game theory around this. There's a lot of game theory went into design, but since we won't have time here, you can read all about it in EAP 1613. Specifically, maybe scroll down to the attacks and mitigation section, which shows exactly shows the attacks and the way we mitigated them through game theory. So we have the Medium article here and the EAP that explains the details. But now I would like to do a demo, and in this demo, so in today's demo, I'm going to do something I haven't tried before. Instead of using our own demo, I'm using, since we started engaging the community and now apps are being built on top of it, I'm going to use an app developed by the Portis team. They wrote a game that uses this, so you can play this crypto game without owning Ether. So I'm going to do a transaction in this game, and then we look at the transaction and see what happened behind the scene. Yeah, so that's the game, and now we are going to try to adopt one of these doggies, and what's going to happen is we need to pay a token for it, and then the address will change and the doggy will become ours. So now as I clicked it and the transaction is going through, what's happening behind the scene is that the web app looked at Relay Hub. It found the relay, looked at the fee, and decided that that's the relay it wants to use now. It sent the transaction to the relayer. The relayer took the transaction and made sure it's going to be paid for using a view function. Once it knows that it's going to get paid, it put the transaction on chain, but it also returned the transaction to us. So here we see that the transaction has already been mined. Before we look at the transaction, I'm going to briefly look at the wallet address. So you can see that there were no transaction on this. No transaction were ever done with this address, which is not surprising considering that it has no Ether, so it couldn't make any transactions. But if we look at ERC20 transactions, we'll see that 1 minute ago, a token was transferred out of this address, which means it had to be done by someone else. So this was done by a relay. Now I'm going to click the transaction. So in the transaction, you can see that the token was transferred from this address, but if you look at the from address, you see a different one. So you see that this relay actually had 5 Ether, which it could use to pay for the transaction. This is the relay. I'm going to copy a part of its address. It will be useful in a moment. Okay, so also let's look at the internals of the transaction. So internally, you see that the transaction consists of 3 different transactions. The first transaction being a static call. This is a call to a view function, where we ask the relayer, we ask the DApp whether it's willing to accept the transaction and pay for it. Once we got confirmation on that, the second internal transaction is the actual transaction, that the adopt transaction that gave us the doggy. And the last call is a post-relay call that tells you tells the DApp how much the transaction ended up costing. And this is very useful if you're trying to implement your own accounting system and charge the user by other means. For example, if you are an ERC20 token, you could let the user interact and transfer your tokens and pay for the transaction using your own token instead of using Ether. So this function tells you how much you should charge the user. Now I'm going to click we see the transaction went to Relay Hub. So I'm going to click the Relay Hub contract. We see all the transactions done here. And I'm switching to the events. So we see that the last event is, it's an event that shows that this particular relay was used on behalf of that address of that user delivering the transaction. But now let's see how did we even find this relay? So I'm going to look at another type of event here. This is the registration event. So when you have, so you see these relay added events. These events are emitted every time a relay registers, or when a relay registers to a relay hub, or when it refreshes its parameters, which happens every once in a while. And you can see that it announced its address, its transaction fee, the stake size, and most importantly, the URL. So I'm going to click this here. Let's see it as a text. So you see, this is the actual URL where the transaction went through. So you see the address of so this is the address of a relay. This is how we knew which relay to talk to. So so what we saw in this demo is how seamless it is for a user to interact with the DApp now, while still retaining the decentralization property that we like, and having the DApp pay for it. And this is all using the gas station network. So thanks Portis for building this great demo. So how do you use this in your own DApp? So how do you use this in your own DApp? You have, in order to use this, you have to make 4 little changes to your smart contract. The first one is you need to inherit a relay recipient. That's a base contract that tells you, that gives you the code you need in order to interact with the relay hub. Then you need to write 2 functions. One function is a view function called accept relay call, which is the way your DApp says whether it agrees to accept a certain transaction from a certain user. And then you need to implement the post relay call, which I explained earlier. This is used for accounting. You can leave this empty if you don't have your own accounting. And finally, you need to change message.sender to the getSender call everywhere. Because message.sender is now the address of a relay, which is not very relevant for your DApp. So getSender gets you message.sender for direct transactions, but for relay transaction, it gets you the real sender. And you can look at this hands-on tutorial that we published, which shows you exactly how to modify your DApp to use this. So recently, we started engaging with the community. To get this to mainnet and to make it the standard for meta transactions. So the first thing we did is we took a burner wallet by Austin Griffith just before ETH Denver. We put it on. We sent a pull request that adds gasless transactions using the gas station network. So if you're using the burner wallet and you have no XDAI to use to pay for the gas, it actually gets paid, and it gets paid by the DApp. So in order to do it, we deployed a few relays on the XDAI network. We've also partnered with Zeppelin, who are now helping us get this to mainnet. So hopefully we'll get there soon. So thanks, Zeppelin. And you saw the demo from Portis. Other projects are also starting to use this. And we are getting support from the Ethereum Foundation now, which is also great, and it's going to speed things up. There's the MetaCartel. MetaCartel is a group that has been working on the meta transactions for a long time, and we have a meetup tomorrow. So you can come there, and we're going to talk a little bit more about this. And MetaCartel is pushing this solution to become the standard. So with that, I think, do we have some time for questions? Okay, that's too bad.
First of all, thank you, great stuff. So how serious is the attack surface where like a malicious actor can kind of extract value from the dApp itself through artificial transactions?
Can you explain the attack? What do you mean?
Yeah, I mean like, so it's not organic usage of the dApp, but some like some attack that is spamming transactions, draining value out of the dApp.
Yeah, so that's what the accept relay call is for. Your dApp doesn't accept random transactions from unknown sources. It can look at the transaction and agree to pay for it. And so if someone sends you a transaction, the relayer can check whether the transaction is going to be accepted and paid for. So if it's a spam transaction, the relayer will not deliver it because it knows it's not going to get compensated for it. And if you have a user that is one of your users and is spamming you, then it's your responsibility as the dApp to remove that user. You can ban him from your. You can have a ban list of offensive users if you have those.
You are telling us to change our dApps to accept relay calls. What about using proxy smart contracts that can be used as identity for the users and that will relay so the dApps won't see any change?
I'm sorry, I could not hear you well.
My question is, what about using proxy smart contracts for user identity that will relay between your relayer and the dApps so we don't have to change our dApp?
I'm sorry, I really can't hear you here.
Maybe we can discuss later then.
No, so, okay, let's, yes. Yeah, definitely, that's one way to do it. So you could have, in that case, the proxy would inherit the relay recipient contract. So you can put a proxy in front of your, a proxy in front of your dApp and have the proxy interact with Relay Hub. That's certainly possible. You still there is one. Yeah, there's. Yeah. You still need to be aware of who the user is. So either you deploy a proxy for each user, which is needlessly expensive, or you need to change the message sender to get sender, because otherwise you don't really know who the user is. It's you need get sender, so you find the real user. All right, thank you.